So last time we had introduced the solubility parameters, talked about the origins of them, the Hildebrand parameter being first for hydrocarbons, and then Hansen coming in and working with polymers, adding in a polar term and a hydrogen bonding term. We'll get into, after these first introductory lectures, how we can determine them. There's a couple of different ways. You might imagine that the polar term is related to dipole moment, so you can make a dipole moment measurement of the molecule, and then you can use sort of a quantitative structure property relationship to turn that into the polar term. You can measure the refractive index of a substance, and that's related strongly to the dispersion term. So this polarizability of the electron cloud, and so there's a conversion that you can use with the refractive index to determine the dispersion term. You can get the total term. That's probably the most easily determined experimental value. You just have to boil the substance and measure the delta H of vaporization. So the delta H of vaporization divided by the molar volume, take the square root, that's the total dispersion term. So if we have the total term, the P term, and the D term, we can find the H term by difference. So that's how the H terms are most often determined. You have the delta H of vaporization, some measurement of the dipole moment, some measurement of the refractive index, and you can then get the hydrogen bonding ability. Some people are bothered by that because they see toluene and benzene and like hydrogen bonding and benzene or toluene. So that's how those values are non-zero, right? Is because they've got the polar term and the dispersion term for those molecules, and they got the total term for the delta H of vaporization, and they're saying, you know, this delta H of vaporization is slightly higher than we would predict just from the dispersion term or just from the polar term. So therefore the H term must be non-zero. Okay, so it's not really measuring how much hydrogen bonding there is in toluene, but it's saying that there's more intermolecular attractions than can be accounted for by the polar and the dispersion term. So the only thing left is this hydrogen bonding term. And it's not like we're saying toluene really hydrogen bonds. It's tiny. It's a small number, but it's accounting for a little bit more intermolecular attraction than can be accounted for by polar and dispersion.
Would a second be underneath the polar term?
Yeah, and so well, I mean, that's going to be your conclusion, I guess, is some way, and so people who see the world from a Lewis acid-base way of thinking will not like the word hydrogen bonding. They like the word electron exchange. And so it's really not electron exchange, though. We're not making ions here, but sort of electron donor, electron acceptor, so that you take hydrogen out of the picture. And so anyway, so that's just different ways that people have explained these terms. But those are the experimental origins for them: delta H of vaporization, dipole moments, and polarizability. And hey, we can calculate all of those with Gaussian. You know, so that is also an option for you in terms of your HSP project, is to find some sort of quantitative structure property relationship from Gaussian calculations to the HSPs. So there's a few papers out there that outline that, of how that's done. We did a really extensive model for the explosives, which I think we put in 25 terms in our model and figured out which ones gave us the best fit to the HSP values. And I think we ended up with about 8 or 9 terms that survived that stepwise linear regression. And we'll talk about that in the last piece of the course when we get to QSPRs. So let's go on with the determination of a solubility or interaction sphere. And you use the term interaction when things really don't dissolve, like a polymer. So a solvent going into a polymer would swell that polymer. So we would call it an interaction sphere rather than a solubility sphere. Or with glass. In this set of notes, we have dropwise interactions of solvents with glass. And they're not dissolving the glass, but they are wetting it. And so that's an interaction sphere, not a wetting or a solubility sphere.
Is your slide supposed to be changing?
No, not yet.
Okay.
So those are all introductory remarks. Essentially, I've told you about these different things. And this is a talk that was prepared, again, by these students who were doing undergraduate research, and then Carl was a master's student for me. And they presented this at the Texas Academy of Sciences meeting, which is sort of a small science society, mostly biology, but occasionally we'll have chemistry talks there, and I've taken students to those. So they presented this at the TAS meeting quite a while ago. But it had a nice set of experimental slides in it, so I wanted to walk through it. We've covered this in the introduction for the Hansen solubility parameters. This, incidentally, is the equation that Jerome, you and I were talking about for the delta H of mixing. And in that homework suggestion, I talk about the maximum delta T for spontaneous mixing. And these are the deltas that I'm talking about. The delta T, so those are the total solubility parameters for 1 and 2. And so what's the biggest difference there that would cause delta H to go up and equal the minus T delta S term? So you can calculate the minus T delta S term by having 50-50 mixtures. You can come up with the mole fractions, and you can calculate the delta S of mixing. And when delta H equals that, then gives energy 0. If delta H is greater than that, gives energies positive. So you have phase separation. So this difference here between those lowercase deltas, that's the thing that's preventing mixing. And so I asked you as one of the problems algebraically just to show what the maximum difference in those total solubility parameter numbers would be to prevent mixing for a 50-50 mixture at room temperature. Did you figure that one out? Or?
Yeah, actually, it doesn't seem too crazy.
Okay, very good. So you did, we were talking later in the day, and so I was just wondering if you had finished that up. All right. So the solubility analysis, you know, this originally was used in paint and coatings. I've used it for solutes like 4-nitroaniline, was doing a sort of an explosive mimic study, and then also used it for surfaces like glass and other surfaces. I've used it for polymer swelling, adhesives. And the point is, we've said in chemistry like dissolves like, but in this case we've sort of had to back off the words dissolves and said like seeks like. So if the solvent is similar to the polymer, it's going to go into that polymer. And if it's similar to the surface, it's going to wet the surface. And so like seeks like just because of the intermolecular attractions. And if you think about just nature in general, it wants to drop in energy. Ball on a hill rolls downhill. The spontaneity is driven by these energy terms. And so if you have similar molecules, them being able to satisfy their intermolecular attractions is going to lower the energy of the system. So if you've got two things that would be connected and they're not, when you make that connection, it's exothermic or it's spontaneous. So now this was converging. So a lot of these, these solubility parameters are listed in tables as megapascals to the 1/2. Okay, and it's because the square of the solubility parameter is the cohesive energy density, which is the delta H of vaporization per molar volume. Okay, so it's an energy per volume. Now, why on earth that Dr. Hansen thought that pressure units was more SI than joules per liter, I don't know. But joules per liter is SI in my book. And so I like to think of these in terms of energy per volume and not megapascals. I show this piece on the slide just to show that numerically they're the same thing. So if you do that conversion and go from pascals to atmospheres, that conversion is 101.325. And then if you go from that atmospheres to joules per liter, it's 101.325. And those conversion numbers cancel. So whatever number, if it's 5 megapascals to the 1/2, that's 5 kilojoules per liter. They're exactly equivalent. So whichever units you want to use, I'm fine with. But you know, the tables, when you look these up in the tables, the units on those tables are megapascals to the 1/2 power. So don't let that bother you. I think mentally it's much easier to think of cohesive energy density, which is energy in volume. And so here's a plot. It's a little dark in here. Maybe if you try to play with the lights. The middle one's down, but let's try to find these right here.
The front ones.
And it's sort of a fun game to play with the light switches. Yay, okay. Does that help? Yeah, so we have these different parameters. You can see water is way at the top. If we just let water go off the top, we can zoom in a little closer. And we see IPA is isopropyl alcohol. Down in front is toluene and hexane. So you can kind of see the different molecules and where they lie. This is plotted, the D-axis is plotted at twice the dispersion term. We talked about that last time. And so the interaction sphere will be a sphere and not a jelly donut. And then the acetonitrile is back in the back. I like this software that I use to plot these. It's called POVRAY, Persistence of Vision Ray Tracing Software, and it's fantastic. So the nice thing about it is you can illuminate these things. So here's toluene. If you wanted to know really how close it was to this x-axis, here's its shadow. You see that? So here's toluene's shadow. So you can turn on shadows and kind of see more about what's going on. Here's ethyl acetate. We know it's in front, but if I wanted to look just in the pH plane, its shadow is right there. And so you can see with the shadows the pH plane. Down here you see the DP plane. And so you can see toluene here. That's giving you an idea how much how polar it is. Over here, its height is how hydrogen bonding it is. So not very hydrogen bonding, not very polar, but certainly not zero. Hexane is 0 polarity, 0 hydrogen bonding. So it's right on that axis. Here's acetophenone. Okay, and so you can kind of see its shadow there, both in the DP plane and in the pH plane. Later on, I got to where I wanted to drop lines down to that plane and made it a little easier to understand, I think, but there's just different ways to play with displaying the data. So let's talk about the solubility sphere, because that's today's item of business. We talked about the Hansen distance, this distance between solute and solvent, or between the two substances, whether it be two solvents when you're trying to determine miscibility, or a solvent and a surface. So anyway, the two things that you're comparing, those are calculated with this distance formula. And then we want to find a sphere that contains all of the good solvents and leaves out all of the bad solvents. So we're going to solve for a sphere for a substance, and we're going to expose it to a bunch of different solvents. And so we will have a substance plotted in this three-dimensional, what I call Hansen space, like Cartesian space, but Hansen space. And that substance is going to have an interaction area around it. And if a solvent is inside that interaction area, it's a, quote, good solvent. And if it's outside, it's a bad solvent. Is that area really, hard, strong, like a phase transition where you cross that barrier and dramatic things happen? Not really. So it's a little bit of a fuzzy area, but it's still a guide in terms of solubility interactions. Now, in order to find that sphere and locate the center of that sphere, we're going to have to use solver. We're going to have to use a nonlinear search algorithm. So in Excel, we have to use solver to guess where the center of that sphere is and how big it is. Well, Excel needs to know what a good fit is. So we need a fit function. So that's what this fit function is. And I'll walk you through the tables and how to build this spreadsheet in the next few slides. But these are the three main equations here. So that fit function, if it's inside the sphere, and it should be inside the sphere, it's a 1. If it's outside and it should be outside, it's a 1. So if we predict that it should be inside and it actually is, we're good. So if we get everything inside that's supposed to be inside and everything outside that's supposed to be outside, then the fit function is 1, and we've got a perfect fit. If we've got a bad solvent inside the sphere, we need to figure out how far in the sphere it is. So we need something that's going to push Excel around, and so we're using this exponential function. So if our distance here, if we look at the difference between R0 and RA, so let's say RA is smaller than R0, we're going to have this term in here, and it's going to reduce our fit. Okay, and it's going to be an exponential dependence. And we're going to have a whole bunch of solvents, and so we'll see this in the spreadsheet, how this works out. So I guess it'll probably be more obvious when we get to the spreadsheet. So how do we determine these? We need some experimental data. And so I've taken a chunk of notes. So if you're following along with the PowerPoint, this next like 8 slides are from the Monday's notes that I posted, just because I thought it was a cleaner example. It's the same sort of spreadsheet examples, but it's a slightly different procedure. So the one on today was for glass, putting drops on glass, and the one on Monday went ahead and showed the solubility analysis, a true solubility analysis. And I thought that made more sense this morning, so I apologize for swapping that on you. But it's just the nitroaniline stuff from Monday's lecture has been put into this lecture because I think it's a cleaner example, okay, than the glass one. So this is the procedure that I used for finding a solubility sphere for, I think it was 2-nitroaniline. So I put in a small amount of powder in a vial, and I added the solvent dropwise and recorded the mass just to have record of it. And then when the solute completely dissolved, then I stopped adding solvent. And then I was able to calculate the percent mass of solute, and so it's kind of a measure of the maximum solubility in those solvents. So, you know, some really small amount of solvent would dissolve it, some quite a large amount of solvent would be needed to dissolve it. And so then we just go through all the different solvents. And so here's the data. So these are the vials, and you can look at these and see that for some of these substances, like for this is propanol, so IPA, 2-propanol. It required quite a bit of IPA to dissolve the substance. And here's hexane. It actually, the hexane was ridiculous. It was way up here. It took a little while for this pictures to be taken, so the hexane has actually evaporated out. Look at toluene, quite a bit of toluene. But look at MEK. You know, that's probably 5 drops of MEK, and it went homogeneous. So it's very soluble in MEK. In toluene, maybe 15-20 drops, almost a mil. IPA, probably 1.5 mils. Not very soluble in IPA, not very soluble in toluene, very soluble in MEK. So you can kind of look at these relative results and figure out which solvents it's good with and which solvents it's bad with. You're trying to determine what the good and bad solvents are. Here's, again, the same trends with more solvents. So propanol, propylene carbonate, you know, those are some bad ones. Here's ethyl acetate. Here's hexane. It never dissolved at all. I mean, it's still just a precipitate in the bottom. Here's toluene. Look how much toluene it had to have before it went homogeneous. So this would be a bad solvent, and NMP would be a good solvent. And so we put this data into the spreadsheet. We have all of the solvents that we tested, and then I went ahead and put in their weight percent. And so small weight percents are going to be the bad solvents, and large weight percents are the good solvents. The Hansen solubility, so this is the real trick with the Hansen solubility parameters and finding this interaction sphere. So let me everybody get their mind on this one point. Trying to figure out the criterion for ranking your solvents is where the magic happens. Okay. I use weight percent and a dropwise, you know, dissolution. If you're dealing with a polymer, you got to figure out swell. Which polymers swell, which ones don't. If you're looking at surfaces, contact angle might be useful. But notice how those are totally different experiments. So that's where the clever behavior comes. That's where you have to solve the problems to figure out what kind of handle are we going to get on this substance. We were dealing with carbon black. It didn't really work. We tried to suspend carbon black in these different solvents, and it just stared at all of them. Right? So we couldn't really get a good handle on which one of these would be a good solvent for suspending carbon black. Apparently you need some other additive that will coat the carbon black and carry it into solution, either as a colloid or something like that. So you know, sometimes you have an idea, you go try it, it doesn't work. Okay, and then you do some more research and try something else. But this is you know, I made it look easy because this worked, but you don't see the times when things didn't work. And so you need to then calculate the distance. So you begin with an initial guess of your solute. So up there we have 4-nitroaniline, and we kind of took one of the good solvents, I think it might have been NMP, and kind of made that as an initial guess in terms of our D, P, and H values for our substance. So we're trying to find the sphere that surrounds 4-nitroaniline, and the good solvents will be inside that sphere and the bad solvents will be outside that sphere. Okay, this Hansen distance, RA, we calculated. So this is so this one right here is using these D values, P values, and H values, comparing it to these. So that's the distance between acetonitrile and 4-nitroaniline. Does everybody follow that? Yeah. And then you go down a row and it's acetophenone compared to 4-nitroaniline. And then the next row is DMF compared to 4-nitroaniline. So those are the distances of every solvent to our solute. And we'll break the laptops out next Wednesday. We'll do this. Okay, so we'll take a data set and we'll actually build our little spreadsheet so we can determine the spheres, so that you guys can use this technique if you wish. Then we have this comparison that we want to compare the distance between the solvent and solute to this interaction sphere radius. So this is an anchored cell in this calculation. I don't see any ones that are less than 1. But if you have a solvent that's inside the sphere, RA will be less than R0 and you have less than 1. So our little radius here is too big. Because even the good solvents like ethyl acetate or toluene, no, let's see, the low, like DMSO, you know, it's less than 1. Yeah. So 1.2 is less than 5. And so when these are less than 1, those are considered good solvents. And then we have, for the fit function, we're going to have to take this difference. And so let's go ahead and calculate a column with this difference. So that's R0 minus RA. So we're anchoring this R0 term up here in our formula. So we're anchoring that cell, we're comparing that to this value here. So the difference between 5 and 7 is 2.4. And then we're going to use that column in our fit function. We need to flag the solvents as good and bad. And so we'll look at these. We're going to choose the ones with a high weight percent as our good solvents. And so we're going to call those solvents good. And the ones that have a low weight percent, we're going to call those bad. So this is where we make that decision. Should you be inside the sphere or outside the sphere? And if you can't get your sphere to have a perfect fit, this is the column that you may want to play with. You may want to decide, see what looks like we decided 19% was our threshold. If it was 19% or bigger, then we would call it a good solvent. If it was less than 19%, we'd call it a bad solvent. But maybe we couldn't, later in the future, we won't be able to find a sphere that has a perfect fit. So maybe our criterion is too tight or too loose. And so you have to fiddle with this good, bad solvent definition, because it's not exactly clear what a good solvent is and what a bad solvent is. Although there's a pretty big jump here. I mean, we have from 15 to 19. But, you know, 15, it's a lot bigger than 10. So maybe, you know, if we couldn't get a fit, we might want to include acetonitrile. And so now for our predicted values. In this case, if our relative energy density difference, this RED number, is less than 1, then our radius is showing that to be inside the sphere. So that would be classified by our model as a good solvent. We chose this one we chose these. Math chose these. Okay. So we can go down there and change those ones and zeros if we want to change what we call good and bad. And then math is going to see if good and bad line up with that. Okay, what is math using? Math is using the location of this sphere.
So all of the RO minus RA values that are negative ended up being predicted by like math. So is it just forwarding that column to the predicted column?
Yeah, I mean, if there's RO minus RA is negative, you're also going to have a less than 1 RED. Yeah, so it's a little bit redundant. And these are just the columns that are lined out in Hansen's treatment. This is how his program worked. Yeah, there may be other ways to shrink it and clean it up. I'm just walking you through. If you were to read his book and he was describing to you how to do this, this is straight out of his book. And that book is linked in Blackboard so that you can get a look at his procedures. Yes.
Quick question. How can you determine weight percent?
Oh, I was measuring it with the pipettes and the vials. So I weighed the vial, and then I weighed out some nitroaniline, and then I added the solvent dropwise. Okay, and so I had the total mass, and then I had the amount of solute that I had at the beginning. So I did all this in my notebook.
So when it's dissolved,
Yeah, so then I'm adding a drop, and I'm looking to see if there's still crystals in the bottom, and if there are, then if there's still crystals in the bottom, then I add another drop of solvent and weigh it, and then I look, still crystals, add another drop of solvent, weigh it, look, and shake it, and the crystals have dissolved, then I stop. And so I know now the total mass that I just weighed, I tear out the vial, and I know the solute that I put in, and I can calculate the weight percent. And so if I only had to put 3 drops of solvent, I have a huge weight percent, because I put a little bit of solute in and I just tiny little solvent, and I've got a homogeneous solution. So I've got a huge weight percent, which is kind of like the max solubility of that solute in that solvent. And then if I'm dealing with, like in that case, toluene or whatever, I had to add 3 mils of solvent before it went homogeneous. And because I had to add so much solvent, it was a low weight percent. Yeah, so then toluene would be classified as a bad solvent in this case. Yes.
Looking at the row right above where it says 0.92, you said that column where it says we chose those numbers, or we chose the solvents. Why was the one right above that chosen?
Oh, interesting.
Was it lower?
The box is in the way.
It's an open-
That's a good. I'm glad you found that, because
It's 20%.
see, it's 20%, and so based on our criterion of anything above 19%, it should be a good solvent. And so we chose, by our criterion, we have to put the 1 there. Okay, so our fit's not perfect. So when we get there, then our predicted doesn't match our flag. So that sol question mark, that's our flag column. We're flagging that column, and then we have a predicted column. And if the predicted and flag don't match, then the fit function calculates the distance. So now this last column is our fit function column. And it's an if-then statement. So we say, if this column equals that column, then the answer is 1. And so the answer is 1 for all of these because they match. We get here, this column doesn't match that column. So then we have to calculate the fit value. And so the first part, if predicted equals soluble, then AI equals 1, else AI equals this exponential term. And so it's this R0 minus RA, which is right here. Change the sign and take e to that value, and that's what we get, 0.013. Okay. Now, how do we get all of that information into a single number? Yeah. So then we just multiply that every row in that column by each other. And so I have a whole bunch of 1s times 1s. So those are going to produce 1, but then we get to that 0.013. And we get, it spoils the fit. Okay,
Until it's
and then we raise that to the 1 over n. So it's sort of like squaring a number, taking the square root, only we have like 20 rows. So we have something to the 20th power, this times that times that times that, take to the 1/20th root. So it gets it back down on the scale of a single number. And so that's our fit value up here, 0.696.
that good.
And we would like that to be 1. And so notice that all of this is built on our initial guess of the sphere location and the radius. Okay, so it's likely that it's not going to be 1. And so we can move this around by hand. We could change the D value and see if the fit goes up. So if we raise the V value, B value, or D value, and the fit goes down, and we go the other direction, and it goes up a little bit. That's tedious because there's 4 dimensions, D, P, H, and R0. And trying to find the sweet spot in 4-dimensional space is tricky, okay? But, you know, computer's way faster than we are. It's doing really not much different than us if we change the values and looked at the fit function. It's got some clever ways to decide what direction it changes those values. You know, I say go up in D, and if the fit function gets worse, go down in D, and then move over to P, go up and down, move over to D, go up and down. But what about the 2 combinations? You know, the diagonals in that space. Excel can have some clever search algorithms for finding, you know, in the diagonals as well. So that's the solver. So that's what we do next. That fit value goes into the target cell. And we want to set that value equal to 1. Did we do solver in any of our earlier stuff? Have we done in this class?
On this class.
In this class, no. Well, then we'll definitely do that next week. Okay. And then we change those cells. We did?
Temperature thing. We had a sulfur temperature. I mean, yeah. the
Oh,
Excel.
that's right.
You showed
You
me
did it
specifically.
and then you showed it to us.
Well, I mean, I did.
Oh, yeah, for the whole function. Yeah, that's right. Okay, but we'll actually get to play with it next week. So then now this is again a technique that I like to use. I don't give Excel all 4 values to play with. I like to play with R.
Oh, because I mean, you can't change those, right? That's what I'm saying. Like, I was gonna ask that too.
What?
You can't like you wouldn't be able to change the actual parameters for nitroanol. You only change the RO.
Well, you can change the position too.
Well,
We're trying to find its position because we don't really know it.
DP and H come from the nitroanol, right?
Yeah, but we're trying to find its experimental.
Oh, so we don't know the.
Yeah, so we don't know the solute
Okay.
or the surface or the paint or the glue.
Okay.
Yeah.
So those are the ones that you just.
Yeah, so those are guesses.
Those are
So I
guesses.
guessed for those 4 numbers, and I'm letting Excel make my guess better. Now, what I'll do is I'll pick a small R0 first, like maybe 2 or 3 kilojoules per liter, and then I'll let Excel change DP and H. So it'll move the sphere around and try to find the best location, and it'll still have good solvents on the outside, but it'll find the spot between all of them. And then I'll slowly increase R. And so I keep doing solver. So I'll slowly increase R, do solver again. Increase R, do solver again. Increase R, do solver again. That's the most stable search algorithm, because sometimes if the sphere's not bounded on one side, it will shove the sphere out into space and R will go to infinity. Okay, so if there's no bad solvents over there, there's no penalty for it moving in that direction. And so you can kind of lose control. Solver will just go crazy on you. And so if you control R and let solver move the sphere, then you have a better control of where it ends up. Okay. And so this is the sphere that I got for 4-nitroanol. You can see the solvents. It'll be more well-defined if I have more solvents. Okay, but this was our data set. It's bounded on the back by acetonitrile, on the front by ethyl acetate, on this side by acetophenone, and in the back by propylene carbonate, and on top by IPA. So those are what's keeping the sphere small. This is actually the minimum sphere. The good solvents are right on the edge of the sphere. I have in the back DMSO, DMF, NMP, and ethyl acetate. And so it's that's the sphere that I've determined for nitroanol. So if I have solvents inside that sphere, they'll interact strongly with it. If I have blends, I can make blends, and we could blend our solvents on the volume fraction weighted component. So if I have 25 mils and 75 mils mixed together, that's a 25-75 volume fraction, and I just take their D values and scale it by 0.25 and 0.75, and I take the P values, scale by 0.25 and 0.75, and the D value and the H values. So it's very easy to blend. Now this is the same sort of analysis, but using contact angle. So here I put drops of different solvents on a surface. I used glass, and this is in the notes for today. We will go more quickly through this because it's essentially the same thing with the spreadsheet. But here, instead of percent weight, I used whether it wetted or not. So you put the drop on there. If it spreads spontaneously, that's interacting with the surface. If it beads up, that's not interacting with the surface. And if it's somewhere in between, I make a judgment whether it's wetting, like a contact angle that's less than 90 degrees, or a contact angle that's greater than 90 degrees. So if it's even a contact angle less than 90 degrees, I might call that a 2. So in this case, I just have 3 levels, 1, 2, and 3. 1 and 2s would be interacting with the surface. 3 would be sort of not interacting. I can't really say hydrophobic, hydrophilic because it's a plastic surface or a glass surface, and I've got solvents on there that are either, they're either wetting glass or not. So this is the same table, same equations, but just using a different score. My scores, 1, 2, 3, are taking the place of my weight percent column. And so when I decide what's a good or bad solvent, I look at those and I call the 1s and 2s good solvents and the 3s bad solvents. So there's the sergeant, bad solvent. And so those are my flags. So you see the 1s and 2s are flagged with 1s, and the 3s are flagged with a 0. So that when I said we choose that column, I'm calling that column's what I'm deciding is a good or a bad solvent. It's just a binary designation. And then we have the predicted column, which comes from the location of the glass solubility sphere. And here we have lots of ones that are not lining up. The predicted and the flags they're not the same. And so Excel's going to have to do some work to move this sphere around. Same fit function. See lots of terms that are not 1.
0.
What's that?
It's so small that it's 0.
Yeah, that's right. It's pathetic. Probably because of that 10 to the minus 5. Yeah. And so I got to move my initial guess around to probably get that to be better. Running solver, we get this sphere. Notice how huge it is because it's really not bounded on the top. The water and the alcohols wet the glass. And so the center of the sphere is pretty far off to the left. And here I've rotated the screen around so that you can see the dispersion axis is in the back, the polar term's coming towards us, and the hydrogen bonding term is going up. So the red solvents are bad, the green solvents are good. If we were to blend these, you can see here, this will tell you that a blend for the nitroaniline, this is the nitroaniline sphere. You know, IPA and toluene, even if they were miscible, okay, is not going to produce a useful blend. But ethyl acetate and acetonitrile would. So this, again, allows us to filter out our options in terms of solvent formulation. And this is a great way to come up with solvent blends. A 3-component blend is a triangle. And so you can use the 3 volume fraction weighted compositions and determine the location in that triangle of like 20% this, 20% that, and 60% the other. Will give you a spot on that triangle. And that might be the good one. And then a 4-component blend that you could take, again, the volume fraction weighted pieces of their DP and H values and find the location of that blend. If you just have a binary blend, you can take the difference, the RA, the Hansen distance, from your solute and compute it along that blend axis. So over on the left, it's kind of like a phase diagram. We have a composition axis. This is the volume fraction of ethyl acetate in acetonitrile. So volume fraction of ethyl acetate, this is pure ethyl acetate. and this is pure acetonitrile. And this is RA. This is the distance of that blend to our solute. So here's our solute here. And here are the DP&H values for solvent 1 and solvent 2. And so we can just do the volume fractions, calculate the DP&H values for the blend, and find the minimum RA. So sure enough, it tells us that a 50-50 blend would be the best option for this particular analyte, for this substance. Not always going to be 50-50, but in this case it just worked out that way. And so here are the references for this. On Monday we'll go through precipitation paths, and we'll look at if we have this nitroaniline and we want to come out, like a lot of times we just use water to precipitate things. And so if we had nitroaniline dissolved in a solvent and we crash it into water, we're going to get crystals. We can look under the microscope and we can see those crystals, and we can see they have a certain shape, a crystal habit. What if we came out of that solubility sphere and went into toluene first and then went to water? Notice we've exited the solubility sphere in a different direction. We've come out the front of that solubility sphere, and now the nitroaniline molecules are surrounded by toluene instead of this blend. And so we've replaced the solvent cage, and then we go to water. Will that have an effect? And so that's the question we'll answer on Monday.